So suppose there's a triathlon competition and you have a river where you have to swim across, there's a cobbled road where you have to cycle across, and then there's a muddy road where you have to run. So this is where you run, this is where you swim, and this is where you cycle. Now you are at this point at the beginning and you want to get to this point. What do you think? What should you do? Do you think that this is your best strategy? Cycle along a straight line oriented towards this end point, disembark your cycle, get into the water, swim across along again a straight line along the same direction, and then go across and run. How many of you think that's a right strategy? If you want to win the race, of course. Anything is a right strategy, as I said. Your cost functional changes, anything becomes a legitimate strategy. You want to lose, anything's a legitimate strategy. But is this a winning strategy? What should be a winning strategy? Subject to your ability. It may still not fetch you a winning time because you might not be a very good swimmer, you might not be a very good cyclist, you might not be a very good athlete who runs very fast. But at least, given your limitations, what do you think you should do?
Velocity of water in its direction, then we account for that and try to get a straight path through them.
So you essentially have to understand your physical limits. What is the fastest you can cycle on a cobbled road? What is the fastest you can swim in a water that has some current? And what's the fastest that you can run on a muddy road? Yeah? And then you decide on certain points, perhaps a point such as this, perhaps a point such as this, yeah? Something such as this. What are you trying to minimize all the while? The sum of this, the time you spent cycling, the time you spent swimming, and the time you spent running. So basically you're trying to minimize this, isn't it? Yes? So the straight line, the shortest so-called path, is not your best strategy if you're trying to win a race. And this is exactly what light does. We shall see in a few lectures from now that this is indeed the case. You can actually prove Snell's law of refraction in an analogous manner. You can solve something even more curious, even more interesting, which is something known as the brachistochrone problem as an extension of Snell's law in the limiting case. Even that we shall see in a few lectures from now. But for now, I hope I have been able to motivate you towards a study of optimal control as to why we should be interested in this particular kind of a problem. Right? Now, to get back to some more mundane and maybe familiar mathematics, the reason being that, as I said, at the end of the day, this kind of a problem is an optimization over infinite dimensional vector spaces, infinite dimensional spaces of functions, right? Let's take a step back. Let's get back to more familiar territory, which is that of finite dimensional vector spaces, and let's look at some of the basic preliminaries. Of course, you know how to optimize a function, as one of you already said when I asked you about the question on fx is equal to x squared. You said, oh, go ahead and differentiate. But I want to ask you to reconsider that when I say that fx is equal to x squared minimized over the interval 2 to 5. Will the differentiation work? It won't, right? What is it that prevents the differentiation from working? The constraint. It's not an unconstrained problem anymore. So you cannot just differentiate, because if you differentiate, you will get x is equal to 0, which is not even part of your domain of interest, right? Okay. So there are things that are lurking within which are still of interest to us. So let's try and revisit. Again, I'll be using the same f which I used for the vector field in the differential equation earlier, symbol wise, right? But this has vastly different meaning. So this is what we are going to be talking about now, fx. Okay. Now, if you give it a moment's thought, you will know immediately that minimizing fx and maximizing minus fx are one and the same thing. So when I talk about it in the language of minimizing fx, I'm not going to be separately talking about maximizing another function fx. The same things that hold true for this would also hold true modulo a certain change of signs as and when needed. Okay, I'll point them out. But the thing is, x now is a vector. Okay, it's not a function of a single variable. It's a function of n variables. Okay, so what we are going to try and look at is a necessary condition for a minimum for fx. Okay, here's the claim that we are going to make. Okay, let's write some of the preliminaries here. I hope you understand what this notation means, right? It means it ingests an n tuple, a vector, and spits out a real number. Okay, that's what f does, right? So we're going to minimize this real number, perhaps, that it spits out. Okay, and let's say so D is a subset of this vector space, this n dimensional vector space of n tuples. Okay, minimum, or sometimes it's called as a minima, can you tell me what it is that you need? Sorry?
Consider an open ball
Yes. And
every point in that ball has a function variable.
right. So when I say a local, when what your friend said here is a epsilon ball, so there exists, okay, that's a symbol for there exists, an epsilon greater than 0 such that how do you put this? I hope you're familiar with the such that for all, okay, let's clean this up a bit. What should be the case? Yes. So that's essentially a way to define it. Doesn't really give us a condition to check. I mean, you're certainly not going to search for epsilon. Let's be pragmatic here, right? Are you going to do that? Are you going to still keep looking at epsilon and in all cases hope to actually come up with a solution like that? If we have some nice properties that we know about f, perhaps we can translate this to a simpler language. Suppose we say suppose do you know what this means? Sorry? Continuously differentiable. It means its derivative is also going to be continuous. If I wrote C0, it would be just continuous. So mod x, yeah, is continuous, but not continuously differentiable. This fellow is continuously differentiable. Yes? So suppose this were the case. Can we translate it to simpler language? Can we get a better condition? What do you think? See, in the previous slide, what we had as D, for instance, it could have been the entirety of Rn as well, if that helps you to think like that. Totally unconstrained, if you'd like to call it. Okay? Okay, before we move on from this slide, let's also look at a certain curious aspect here. I have written local minima here, right? What does that tell you? There is no requirement that this fellow has to be unique. In fact, it need not be unique. For uniqueness, it should be there has to be exactly one local minimum. However, is it possible in that case that this inequality, this relaxed inequality still holds? What would you need in its place? You need strict inequality here, isn't it? This relaxed inequality doesn't cut it. Yeah. So you cannot have a function attaining the same value along, say, a certain number of distinct points, or maybe along some trajectory, along some curve. If the function attains the same value, then there's no hope of having a unique minima, right?
There can be points outside D which belong to that epsilon.
Well, for the moment we are just talking about the domain D. If you wish to extend D and consider everything, that's the second aspect of global. If you want a global minima, you'll have to allow this D to cover the entirety of Rn. So as I said, there are two things. The first thing is this has to be tightened. A global unique you need, right? You cannot have this global unique result without both of these factors being taken into account, that the D must include the entirety of Rn. Only then the question of globality arises, because otherwise you are looking within some restricted domain inside Rn, inside this n-dimensional Euclidean space. So for a global result you need to have this entire Rn. Yeah, and you also need the strict inequality. Yeah, that's when you have a unique global minimum. Yeah, but let's now get back to what kind of a benefit we can harness if this is the case. Yeah, suppose D is an open set. How many of you are familiar with the idea of an open set? Okay, so since we are dealing with Euclidean spaces here, I'll just put it in a very simple term. An open set is a set that does not contain any of its boundary points. I wonder if that still makes things clearer. Let's take the simplest case of an interval. An open interval, I'm sure everyone knows what an open interval is. What is it that distinguishes the open interval between 0 and 1 with the closed interval between 0 and 1? The points 0 and 1 are not part of the open interval, which means what exactly? No matter how close you get to 1 from the left hand side, or how close you get to 0 from the right hand side, there will always be an uncountably infinite number of points to your left as you approach 0, and an uncountably infinite number of points to your right as you approach 1. Which means in the one dimensional line, a ball is something that looks like an interval, right? So you can always have an open ball around every point in an open set. Yes? So points that are interior, every point is an interior point essentially. There is no point in an open set that is a boundary point because the boundaries are not included, right? So if D happens to be an open set, then every point that you choose inside D and try to test as to whether that is a candidate point for a minimum, you can always draw a ball around it, and that is very, very crucial. So suppose I also say D is an open subset of Rn. Yeah, so that you're allowed to draw this ball. I'm just trying to make life simpler so that calculus can take effect, essentially. Later we shall also relax this and we shall also consider points at the boundary and see how these conditions can be modified. Okay, all right. So does anybody know what the condition is that we need to test or we need to investigate? A necessary condition for it to be a minima. Within this setting now, if you invoke calculus, yes, so what is the definition of derivative for this f, a multivariable function? Gradient, fantastic. So the condition is grad of f is equal to 0. This is the condition that you are essentially going to look at satisfying at x is equal to x star. Why is this going to be the condition to zero in on or focus on? Why should this be true? Any idea? Limit, but now there are limits that can be approached along several different directions, no? So what do?
You can consider each direction as a derivative.
Are you going to do that with every possible direction?
No, just the basis.
And then?
And any linear combination will be.
Yeah, but then why should this be the case? Why should the grad of f be the case? You see, f was a function to begin with. F spits out scalars. Grad of f is a vector. Why should each component of this fellow be 0? When you're saying this is 0, remember, grad of f is what? If you have f of x1, x2, dot 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 till xn, that's what this is. Yeah, whether you write it as a n tuple or you write it like this. So grad of f is going to be defined in this manner. In fact, I'm going to write a shorthand notation here. F xi is going to be defined as dou f dou xi. So when you are saying this is 0, you're essentially saying that all of these fellows are 0. That's along every possible component of this. What we are going to do here is something that will take us back to single variable calculus. How so? Okay, so let us consider, okay, since I have no better thing to do than to draw things here to represent stuff, let's consider this as x star. If you want to go slightly off this point x star, let's say to a point here, what you've essentially done is probably something like this: x star plus alpha times v. What is v? V is, suppose, a unit norm vector along this specific direction. Yeah. So this is your v. What is alpha telling you? The amount of excursion you have taken from x star. The distance that you have traversed from x star is what is being denoted by alpha here, because v is a unit norm vector already. Yeah. So if you are making alpha very small, then you are staying within some small neighborhood around x star. Okay, good. Let's define. So we shall just define this function and let you think about this until we meet tomorrow for the next lecture. But let's define this g of alpha as f of x star plus alpha v. What is alpha? Alpha is a scalar. Yes, we are all agreed on the fact that alpha is a scalar. X star is a vector, of course, but it's a fixed point. Bunch of numbers, n numbers. V is also a fixed direction that you have assigned. Once you have assigned this, this gets fixed up. The only thing varying in this entire argument here is this fellow. It's alpha, telling you how far you have gone from x star. So if indeed x star is the point of minima, what should happen? How should that translate in terms of alpha? At what point of alpha is the minima attained? At alpha is equal to 0, fantastic. So now we have brought the focus back from f at x star to g at 0. Yes, suddenly the problem has been turned from looking at a problem in n-dimensional vector space to the space of scalars such as alphas. Yeah, how does that help now? Well, we know the standard extensions of these functions of single variables in terms of Taylor series and what have you. Yeah. There is one small point here though. You fixed v. X star, okay, I am checking for whether x star is a minima, so x star has to be fixed. But here you have fixed v. Are you going to be checking at all possible v's? We shall bring that back into the picture right at the end. For now, let us just focus on this one direction which is v, and we shall see that how by expanding this g of alpha, by taking alpha to be very small, which is reasonable after all because we are only looking at finding a small possible epsilon, no? So we are going to expand this g alpha in a Taylor series around alpha is equal to 0. Yeah, and then we are going to try and find out what must needs be satisfied in order that g of 0 is indeed a minima for this function g. Yeah, so when we come back for the next lecture, that's precisely what we're going to try and zero in on, and we shall eventually reason out that this is indeed the necessary condition, the necessary first order condition for optimality of a point x star for the given function, that is f in C1. Okay, thank you.